one hormone released in pulses every 60 to 90 minutes controls almost everything downstream in reproduction.
Yeah, and if you get that rhythm wrong, the whole system just completely stalls.
Right. So you are listening to a deep dive into the hypothalamic pituitary-gonadal axis. It's essentially the biological control tower of human reproduction.
It really is.
And today we're figuring out exactly how this invisible physiological rhythm dictates everything downstream. And, what happens at a cellular level when medical science decides to just hijack that rhythm.
Which is a phenomenal mechanism to study. I mean, because it requires us to think about biology in terms of time. Right? Rather than just chemical volume.
Yeah, timing is everything here.
Exactly. So to establish our roadmap for you, this axis operates as a strict 3-level chain of command.
Like a corporate ladder.
Pretty much.
Yeah.
At the top, up in the brain, the hypothalamus acts as the commander-in-chief.
Okay, the boss.
Right. Then below it, the pituitary gland serves as the general. It receives the commander's signals and dispatches chemical orders into the bloodstream.
And then at the very bottom.
At the bottom, you have the gonads, so the ovaries in the female system. They act as the soldiers executing the actual mission.
So brain to pituitary to ovaries.
Right. And the complexity and, frankly, the genius of this system lies entirely in how these 3 levels communicate through carefully timed feedback loops.
But if the hypothalamus is the commander, its orders mean absolutely nothing if they aren't delivered in the correct format.
Oh, absolutely. Format is everything.
Because the source material emphasizes that the hypothalamus secretes gonadotropin-releasing hormone, or GnRH, into these specialized blood vessels connecting it to the pituitary.
Yes, the portal system.
Right. But it's not a steady flow. It is secreted in strict, distinct pulses, roughly every 60 to 90 minutes.
Yep, a very strict rhythm.
So why rely on a rhythmic pulse instead of just a continuous flow of hormone? I mean, if the brain wants to send a strong signal, wouldn't a heavy, constant stream of GnRH be more effective?
You would think so, right. But in endocrinology, a continuous signal often just leads to a dead end.
Really? Why is that?
Well, to understand why, we have to look at the cellular receptors on the pituitary gland itself.
Okay, the receivers.
Right. These are G-protein-coupled receptors, and they're specifically designed to bind with GnRH.
So the pulse hits them.
Exactly. When a pulse of GnRH hits these receptors, they activate, they trigger the internal machinery of the pituitary cell, and then, and this is crucial, they need a period of silence.
Silence, like they just need a break.
Basically, yeah. They need that 60 to 90-minute gap to reset and prepare for the very next chemical signal.
Huh. So what happens mechanically if that gap never comes?
If it never comes.
Yeah, let's say we override the system and just administer GnRH continuously. Does the pituitary just keep firing its own downstream signals nonstop?
Actually, it does the exact opposite.
Wait, really? It stops?
It stops completely. If the GnRH signal is continuous, the pituitary receptors become overwhelmed. The cell recognizes that the signal is essentially stuck in the on position.
Which I'm guessing is bad.
It's biologically dangerous. So the pituitary cell initiates a process called downregulation, or receptor internalization.
Internalization, like it hides them.
Literally, yes. It pulls its own GnRH receptors inside the cell membrane. It removes the antennas from the roof, so to speak.
Oh, wow. So even though the hypothalamus is screaming its orders, the pituitary has completely deafened itself to the sound.
Exactly. The entire reproductive axis stalls because the signal lost its rhythm.
That is wild.
Yeah.
I mean, to use a sensory parallel, it's sort of like a drummer keeping a steady, powerful beat.
I like that.
Like you can anticipate it, you can move to it, and your brain processes each strike individually.
Right, you hear the music.
But then imagine someone just leaning their elbow on a synthesizer key, producing this continuous blaring wall of sound.
Oh, yeah, that's terrible.
Very quickly, your brain stops processing the note as useful information, and you instinctively cover your ears to block the noise.
That is a perfect analogy. The pituitary gland is doing exactly that. It requires the silence between the beats, just as much as it requires the beat itself.
That structural reliance on rhythm is just fascinating to me.
It's elegant.
But a metronomic beat in the brain doesn't physically build an oocyte down in the ovary.
No, it does not.
So how does the pituitary gland translate that GnRH rhythm into actionable physical construction at the gonadal level?
Well, when the pituitary receives a healthy, pulsatile GnRH signal, it responds by releasing 2 distinct gonadotropin hormones into the bloodstream.
Okay, what are they?
Follicle-stimulating hormone, or FSH, and luteinizing hormone, or LH.
FSH and LH.
Right. And these two hormones travel down to the ovaries and operate under what we call the two-cell, two-gonadotropin model.
2 cells, 2 hormones.
Exactly. They have completely different targets, but they are entirely mutually dependent.
So let's break down that 2-cell model. We have follicle-stimulating hormone targeting the granulosa cells of the ovarian follicle, right?
Right.
And luteinizing hormone targets the caucus cells on the outside of the follicle.
You've got it.
The clinical texts kind of describe this interaction as a localized manufacturing process.
It's a very industrial process, actually.
Yeah, so if we view the follicle as an industrial refinery, how do FSH and LH divide the labor?
A refinery is an excellent framework for this. So in this model, think of LH as operating the oil rig.
Okay, the extraction.
Right. LH binds to the TECA cells and triggers steroidogenesis. The ECA cells take circulating cholesterol and convert it into raw androgens.
Like testosterone.
Primarily androstenedione and testosterone, yes. But those raw androgens are essentially crude oil.
Unrefined.
Highly unrefined. The follicle cannot use them in that state. In fact, high levels of unrefined androgens are toxic to the developing follicle and will actually cause it to arrest.
Oh, so LH is extracting all this crude oil, but it has absolutely no capacity to refine it.
None at all.
That must be where FSH comes in.
Exactly. FSH is building and powering the refinery itself.
Okay, how does it do that?
It binds to the granulosa cells,
Well,
causing them to proliferate and expand the physical structure of the follicle.
so it literally builds the building.
Yes. But more importantly, FSH induces the production of an enzyme called aromatase inside those granulosa cells.
And aromatase is the machinery that refines the crude oil.
Yes, the PEPICA cells hand over those raw androgens to the granulosa cells.
Okay.
And then the granulosa cells, powered by FSH and utilizing aromatase, convert those androgens into estradiol.
Which is the primary estrogen.
Exactly. So you see, the two hormones must work in perfect synergy.
Because if you don't have LH,
If you don't have LH, you have a massive, well-staffed refinery with absolutely no crude material to process.
and without FSH.
Without FSH, you have a toxic buildup of crude androgens and no machinery to convert them into the estrogen that's necessary for the oocyte to survive and mature.
It's brilliant. But okay, once that refinery is up and running, producing high volumes of estrogen, the gonads have to report their progress back to the brain.
Oh, they have to. Otherwise, the pituitary would just keep pumping out FSH indefinitely.
Which brings us to the feedback loops.
Yes, the control mechanisms.
So for the vast majority of the cycle, the system operates on negative feedback,
Right.
meaning as the follicle grows and produces more estrogen and inhibin B, those hormones travel back up to the brain and tell the pituitary to lower its production of FSH.
Which is a brilliant, albeit kind of ruthless biological mechanism.
Ruthless how?
Well, humans are evolutionarily designed to carry a single pregnancy at a time.
Yeah.
But at the start of a cycle, a whole cohort of follicles begins to develop simultaneously.
Right. A whole bunch of them.
Exactly. So the body needs a way to select exactly one winner from that entire cohort.
And it does that by deliberately restricting the very hormone the follicles need to survive.
Yes,
It's essentially an efficiency contest driven by a shrinking budget.
that is the exact mechanism. By dropping the systemic FSH levels via negative feedback, the pituitary literally starves the developing cohort.
So the weaker ones just die off.
Right. The smaller follicles, the ones which haven't developed enough FSH receptors on their granulosa cells, they can no longer sustain their internal refineries.
Because the budget got cut.
Exactly. So they undergo atresia, which is programmed cell death.
Wow.
But one follicle, the dominant follicle, will have proliferated enough granulosa cells and enough receptors that it can continue to thrive on the incredibly low concentration of FSH left in the blood.
It survives because it is the most highly optimized structure in the ovary.
Exactly. It outcompetes all the rest of the cohort.
But here is the paradox that seems to contradict the basic laws of this system, at least to me.
Okay, let's hear it.
So for weeks, estrogen acts as the suppression signal.
Right, negative feedback.
More estrogen equals less FSH and less LH. But eventually, that dominant follicle has to release the oocyte.
It does.
And to do that, the system switches to positive feedback, where high estrogen suddenly triggers a massive surge of LH.
Yes, the LH surge.
But if estrogen has been the off switch this entire time, how does it suddenly become the on switch? I mean, the pituitary gland doesn't just change its mind.
No, it doesn't. And it is one of the most remarkable threshold events in human physiology, really.
So how does it work?
To understand the paradox, we have to look at what estrogen has actually been doing inside the pituitary cells during those 2 weeks of negative feedback.
Okay, what has it been doing?
While estrogen suppresses the release of LH into the bloodstream, it actually promotes the synthesis and storage of LH inside the pituitary.
Wait, really? So the pituitary is secretly stockpiling luteinizing hormone behind a dam, even while it refuses to release it into circulation?
Exactly. The pituitary builds up this massive reserve.
Hmm.
Meanwhile, the dominant follicle is growing larger and its estrogen production is increasing exponentially.
Because the refinery is getting huge.
Right. And when that estrogen concentration hits a very specific high threshold, typically around 200 picograms per milliliter, sustained for roughly 50 hours, it activates a completely different cellular pathway.
Okay, what happens then?
This sustained peak radically hypersensitizes the pituitary receptors to the GnRH pulse.
The dam breaks.
The dam completely shatters. That sustained high estrogen flips the cellular logic entirely.
So the next time GnRH hits,
The hypersensitized pituitary responds to the very next GnRH pulse by dumping its entire stockpiled reserve of LH into the bloodstream all at once.
and this is the LH surge.
This is the LH surge.
And that surge physically forces the dominant follicle to rupture, releasing the oocyte.
Yes, but there's a critical step there.
Right. The source material makes a crucial distinction regarding the maturation of the oocyte itself.
Yes, the LH surge doesn't just burst the follicular wall.
It chemically resumes meiosis inside the egg, right?
Exactly. It forces the oocyte out of its arrested state and pushes it to the M2 stage of maturity.
Which is super important.
It's a non-negotiable safeguard. Because without reaching the M2 stage, the oocyte simply cannot be fertilized by a sperm.
Right.
The biological brilliance here is that the LH surge, the trigger for M2 maturation, can only occur if the follicle is capable of producing massive, sustained amounts of estrogen.
Oh, I see.
And it can only produce that much estrogen if its internal refinery is perfectly constructed and fully mature.
So the body basically guarantees that ovulation only happens when the oocyte is absolutely primed for fertilization.
Exactly. It's quality control at its finest.
So we have this elegantly ruthless system. The hypothalamus caps the metronome, the pituitary sends FSH to build the refinery and LH to extract the raw materials.
Right.
The negative feedback loop starves out the weak to select one dominant follicle, and the positive feedback threshold triggers the release of an M2 mature oocyte.
A perfect summary.
But what happens when we need to change the rules of the game?
Clinical intervention.
Yeah, in clinical applications like ART-assisted reproductive technology, such as IVF, the goal is not a single oocyte.
Well, that was definitely not.
The goal is to retrieve multiple mature oocytes to maximize the chances of a successful pregnancy. So how does medical science negotiate with a biological axis that is aggressively hardwired to only produce one?
Well, you cannot negotiate with the axis.
No.
No, you have to completely disconnect it.
Wow, okay.
Yeah, if a physician were to simply administer exogenous FSH to a patient to stimulate multiple follicles simultaneously, the intact feedback loops would instantly ruin the cycle.
Because if you have 15 growing follicles instead of one, you have an industrial-scale refinery producing 15 times the normal amount of estrogen.
Exactly. The blood estrogen levels would completely skyrocket.
And how would the pituitary interpret that massive estrogen spike?
Think about the threshold we just talked about.
It would read that spike, assume the follicles are fully mature, hit the positive feedback threshold prematurely, and trigger an LH surge.
Exactly. The LH surge would fire days or even weeks too early.
Which would be a disaster.
A total failure.
Mhm.
The oocytes inside those follicles would not have enough time to naturally develop, they would not reach the M2 stage, and they would be entirely useless for fertilization.
So to prevent this premature positive feedback loop, the medical team has to put the control tower on manual override.
Right, by severing the communication lines between the brain and the ovaries.
So the sources outline two primary pharmacological tools used in ART protocols to achieve this blockade. Right.
Yes.
GnRH antagonists and GnRH agonists. Mechanistically, they achieve the same result silencing the pituitary, but they get there through very different pathways.
They do.
The GnRH antagonist seems pretty straightforward. It acts as a direct competitive blocker.
Right. It physically occupies the pituitary receptors, so the natural GnRH pulses just can't bind.
So an antagonist puts a deadbolt on the door.
That's a good way to put it. The suppression is immediate and profound. The agonist, however, leverages the exact vulnerability we discussed at the very beginning of this deep dive.
Wait, the pituitary's absolute reliance on rhythm.
Exactly.
This goes back to the synthesizer analogy.
Yes, it does.
So a GnRH agonist is not a blocker. It's a synthetic version of the hormone that binds to the receptor and refuses to let go.
Exactly. When the agonist is administered, it binds to the pituitary receptors and delivers a massive, unyielding, continuous signal.
And initially, the pituitary reacts exactly as you would expect, right?
Yeah, it panics and dumps all of its stored FSH and LH into the bloodstream.
Which is known clinically as the flare effect.
Right, the flare. But because the agonist provides a continuous signal with no 60 to 90-minute silent period.
The pituitary cells quickly initiate downregulation.
Yes. They pull the receptors inside the cell membrane to escape the noise.
They internalize the receptors, the pituitary becomes completely desensitized, and its internal production of gonadotropins just drops to zero.
Yeah. So whether the clinical team uses an antagonist to lock the door or an agonist to deafen the receptors, the result is the same. A silenced pituitary.
The natural LH surge is impossible.
Completely impossible.
So now the physicians can fly the plane manually.
Exactly. Now they take control.
They provide specific daily doses of exogenous FSH to drive the simultaneous growth of a whole cohort of follicles safely.
Right.
But eventually, those follicles still need the equivalent of an LH surge,
Yeah.
right, to resume meiosis and reach the M2 stage for retrieval.
They do. They need the fire alarm.
And since the patient's own pituitary is offline, the clinical team has to simulate that fire alarm pharmacologically.
Right. So when ultrasound monitoring confirms the follicles are the correct physical size, the physician administers a trigger shot.
Right. The notes mention this trigger shot is often an injection of HCG, human chorionic gonadotropin.
Yes.
But why use a pregnancy hormone to simulate an ovulatory surge? Why not just inject synthetic LH to do the job?
That's a great question. It comes down to molecular structure and biological half-life.
How so?
Well, HCG and LH are incredibly similar. They share an identical alpha subunit and a very similar beta subunit.
So they basically look the same to the body?
Pretty much. Because of this structural mimicry, HCG binds beautifully to the exact same LH receptors on the loci and granulosa cells.
Oh, I see.
But crucially, HCG has a significantly longer half-life in the bloodstream than LH does.
Ah, so injecting LH might give you a quick spike that just fades too fast.
Right. It might not be enough.
Whereas HCG guarantees a robust, sustained signal that ensures every single follicle gets the message to push its oocyte to the M2 stage.
Precisely.
Yeah.
It provides a highly predictable engineered surge.
That is so smart.
Yeah, so the oocytes resume meiosis, they reach the M2 stage, and the clinical team schedules the surgical retrieval for roughly 34 to 36 hours later.
Basically intercepting the oocytes just hours before the follicles would naturally rupture.
Exactly. By mapping the exact cellular logic of the HPG axis, medical science figured out how to safely shut down the metronome, optimize the ovarian environment, and bypass profound biological barriers to fertility.
It is honestly a staggering application of physiology. I mean, taking a system designed for singular efficiency and manually expanding its bandwidth to create multiple chances at life.
It really is a marvel.
Let's do a rapid recall of the core mechanisms we unpacked today for you, just to anchor this architecture in your memory.
Let's hear it.
Number 1. The LH surge is the ultimate trigger for ovulation and M2 maturation. And it's driven by a rare positive feedback threshold where stockpiled LH is released in response to massive estrogen.
Thought on.
Number 2. The two-cell model acts as a refinery. LH drives the Maury cells to produce crude androgens, while FSH drives granulosa cells to convert those androgens into estrogen via aromatase.
Perfect.
And number 3, at the very top of the tower, GnRH must operate as a metronome. It has to be released in pulses every 60 to 90 minutes. Otherwise, the pituitary internalizes its receptors and the entire system goes deaf.
Those are the absolute foundational pillars of the female reproductive axis. But I want to leave you with a final physiological puzzle to consider.
Ooh. Oh.
Today, we mapped a system defined by dramatic peaks and valleys, right? Building a complex follicular structure, triggering a massive ovulatory event, dismantling the remains, and then completely resetting the baseline every single month.
Right, a cycle of constant revolutionary change.
But what happens if we apply this exact same three-level biological blueprint, hypothalamus, pituitary gonads, to a system that is not allowed to reset?
Right, not allowed to reset at all.
Right, a system that doesn't operate in monthly cycles, but instead is tasked with running a relentless, unyielding marathon, producing millions of microscopic structures 24 hours a day, 7 days a week, for decades on end.
Wow. And that marathon is precisely what we are going to unpack in our next deep dive when we explore how this identical control tower operates on the male side.
Yeah, it's going to be fascinating.
We will focus on the mechanics of local testosterone, the precise stages of spermatogenesis, and how C1 and C2 development relies on these very same signals.
We'll even delve into surgical interventions.
Right, like TC, for when the localized system needs to be bypassed entirely. Thank you for joining us on this deep dive into the control tower. Keep analyzing the rhythms behind the biology, and we will see you next time.